Welcome to the second of our practical physics walkthroughs, designed to prepare you for your lab sessions and just help you get the most out of it. Today we're going to be looking at springs in series and parallel, which is week 2 of our introductory experiments. Really looking at helping you take careful measurements today. You're going to be plotting a graph and crucially finding the spring constant. And just doing it in a few different contexts so you can actually make comparisons between your different readings. Before you start this, you might want to you definitely will want to have looked at the lab script before the lab and had a little look at what the aim is and a little bit of the theory behind it. You can see there's not too much. If it's a bit of theory that you can't remember from GCSE, and Hooke's law was on GCSE, then on Godomy Online there's a link to the textbook ebook. And just so you can see where that link is, move you out the way, right at the top of Godomy Online it says Dawson Era ebooks, and you click on this link, and if you're in college it will just open it up. At home you'll have to log on, but there's a full description of how to do that here. So you then search for Hooke's law in the book and you will find this section of the ebook, and you can have a little read through and you can see it's got the classic experiment and even talks about springs in series and parallel. It even actually gives you a bit of theory and a bit of experimental data just for you to actually see how, as far as we need to go, how this experiment's going to go. So we're going to do this experiment, and we're not going to follow this particular script. We're going to use the one that's going to be available to you in the lab. And the basic gist is you're going to do 3 experiments. One, the standard Hooke's law experiment that you've almost certainly done before. One with 2 springs in parallel, and one with 2 springs in series. That will get you 3 values for K, and you'll be able to compare them. So our method is really short, but just because it's a short method doesn't mean that you should rush it. You need to think carefully about how you're going to do it, and it's not the measurements you're going to take, they're absolutely bonkersly easy. It's how you take them and get a careful value. That's the important thing. So I'm hoping that the front page will already be stuck into your lab book, and ideally you've already written out this this table, and if you're clever you should be able to set out this table so you can take all of your readings in one table. Don't have to, but you certainly could do. One thing you might not have done at GCSE is taking a value for both the loading and the unloading, and when I go through the experiment I'll show you exactly what I mean by that. This gives us 2 values very quickly for the same load, and that means that we can average it and get a slightly more reliable reading. So all the equipment's going to be given to you on a tray. So you've got some 50 gram masses, a couple of wooden dowels, a half-metre ruler. I think it says a metre ruler, but we'll probably give you a half-metre ruler, set square, and a couple of springs. Also going to give you a clamp stand with a couple of bosses and clamps, and we expect you to set this all up yourself. And for the first experiment you're just going to do 1 spring. Pause that for a second. So let's have a little close look at how I've actually done this. On the diagram it shows you taking a measurement from the bottom of the spring. Well, you can do that, but it doesn't actually matter where you measure it from. So my personal preference would be to measure it from the bottom of the mass hanger. If you get that ruler really close and then adjust it so that you've got it bang on a obvious point. So I've got that bang on 30 centimetres, you can see. And then you've got your eye absolutely level. You don't really need the set square. I mean, yes, you should use it just to be sure, but that is absolutely bang on. Do make sure that this isn't rubbing on the ruler, because that will make a difference. So now what you're going to do is take a series of readings, and that's effectively zero mass. Put 50 grams on. Get my eye nice and level. I'm just use set square just to be sure. And I can see that that is now 32.2 centimetres. Take off the original 30, 2.2 centimetres. Dead easy. Do that for the rest of the masses, and of course you're going to then record that in your table. If you are sneaky about how you lay out your table, you could do it like this, so that you know you're going to do 3 experiments, single, parallel and series. You're going to use these mass values and therefore load values for the same. You can start it at the same point every time. That's in your control. So if you're doing all of that, then you can say, okay, my extended position this time was 32.2. Fill in all the others, and well, I'm going to show you a second to do the unload, but you can actually calculate the average and the delta L for each. So you might have to do this, turn your lab book 90 degrees. There's nothing wrong with doing each one individually, but just saves you copying this out 3 times. So I just want to have a little look about why we're doing this load and unload. If we cut to this, I'm just come back a little bit. If I load, just don't let it bob up and down too much. Take a reading, load, take a reading. Notice how I'm holding the hanger as I load it. So I'm letting it go down to its extension and then reading it. And we'll pretend that that's 7 extra readings. I'll only have 1 reading for the bottom reading, but now when I take this one off, again I can just let that come up. I'm just going to lift it up, lower it down again, and just wait for my finger to move away. I can now take a second reading at eye level from that point. Same again, so take a reading, take a reading. Now at this stage, don't want that bobbing up and down too much. We're now back to our first reading, just 50 grams. I can read this off again. Actually, it's just 1 mil different. Actually, it's 32.3. So that's fine. I would just go back to my value here and do 32.3. And I'd work out my average. So obviously that's 32.25. Okay. So my average delta L is 2.25. Obviously not. I've just realised. I've actually put this up in meters here because that's what it says on the sheet. I would never do that. Bosh. Centimetres. I always record in the unit that I'm measuring, either millimetres or centimetres, or if I'm measuring in meters, I'm measuring in meters. I don't do any unit conversions when I'm writing down. Now, for this average, I could do it in centimetres, or it's not a bad thing to convert it into meters at this stage, as long as you just remember to do conversion correctly. Now, in all of this, I'm being really, really careful to make sure that my sig figs remain consistent. So I'm measured to the nearest gram, so I'm recording to the nearest gram. This is a little bit awkward because I want to measure to 3 sig figs, but let's think about it. If I add 1 gram to here, because to get to the force I'm timesing it by 9.8, roughly timesing it by 10, then in actual fact it's a 0.01 change in the force. So this is the correct number of sig figs. This 0 here is sort of significant. It's not significant obviously, but is effectively significant. So I'm recording it to 3 sig figs, but obviously for these values there's only going to be 2 decimal places and a leading 0. So you just need to be careful because the number of significant figures that you record to expresses the precision to which you took the measurement. And that is vital that you carry that through. So here I've got 3 sig figs, 3 sig figs all the way through. Here, because I've taken an average, I'm going to keep this extra 1. I don't really want to round it at this stage because I'm going to be doing something with it. But I've ended up with 3 sig figs in my final delta L. I would want to keep that number of significant figures consistent because it expresses the level of precision. Now obviously for this loading and unloading I would go through and fill in all of these values first as I load, adding 50 grams each time, and on the way back up I'd record all the unloading values. And that's how you do the first experiment. And if you're smart, one of you is doing the readings. In fact, definitely one of you does the readings because you'll be working in pairs. And the other one is doing the recording. Then for the parallel, swap over, gives a chance for the other person to catch up and record these down. Right, let's just quickly look about how you actually set up this parallel sort of set of springs. So for the single spring, we just got it hung off this hook at the end of the dowel. That's all really easy. For the parallel, we're going to have to use the dowel slightly differently. Okay, so you can see the setup. I've got 2 wooden dowels. Whoops, get slightly focused. 2 wooden dowels with 2 springs in parallel, and then we've got that little bit of red wire that's got our mass hanger hanging off it. I'll put a few mass on there just to even this up. And hopefully you can see about how that has been arranged. I've taken the ruler off for a second. Now you also notice that the 2 springs aren't quite level, aren't quite stretched evenly. So all you have to do is just, it says here's where it all falls to pieces, is just carefully move that little red hanger here. Just make sure this is level as well. Find something horizontal in the lab that you can do it off by eye. You want to make sure these 2 springs are vertical so the one isn't flaring out. And hopefully I've now got the 2 springs being stretched evenly and the 2 wooden dowels being parallel to each other and ideally horizontal. At this stage you can replace your ruler, move it back in position, and then adjust these up and down to make sure at the bottom of this, and clearly we're going to need to. So I've actually had to add an extra 50 grams for this, for my zero reading, because otherwise I've ended up being compressed. So I'm going to take that as my 0. Rearrange this so that I've got my 30 level again, or it could be whatever, it doesn't matter what you choose. And that way, when I add this, I'm going to just adjust this so that it's nice and close again. I don't think I'm going to be able to get close enough to do this without the set square. Obviously make sure my ruler is vertical. Lovely. And now I can just use the bottom of the masses, whatever it happens to take, because that isn't vertical at the moment. Okay, now it is. And I can take it off from the bottom of the masses and then read it off from the ruler exactly as I was doing previously. You can then record that in this table, exactly the same way as you did for the single, fill it in, and you'll get a set of delta L's, which is what we're after, a set of extensions. Same again for the series. What you're going to do is set it up, but this time it looks like this. So I've actually reversed the order of the ruler, so I'm a bit higher up. I suppose you could do this from the start, because this is going to extend much further, and of course being 2 springs it's longer. It doesn't really matter which order you do these 3 experiments, but each one is exactly the same. Add a mass, carefully allow it to extend, try to avoid any bobbing about too much, and carefully take the reading off from the ruler. Add another mass, take the reading, add another mass, take the reading, and then do exactly the same in reverse so that you unload it as well. When you've done that, you should end up with something that looks a little bit like this. This is, I'll show you somebody's lab book. So here they've stuck it in, and they've actually gone for 3 separate tables. So you've got the single, parallel, and the series, and you can see that they've been they've been consistent with their sig figs. This ideally would have been add an extra 0 to it, because that should be, it's 50 grams, it's the nearest gram, so we should have an extra sig fig there. That's fine. Also, they haven't really done enough readings. 1, 2, 3, 4, 5. You're looking for 8 readings. You might only get 7 out of 1. That'll be okay. Obviously, we don't want to overstretch the springs, but as long as you not damage the equipment, you want to try and get as wide a range of readings as possible. And once you've got all of those readings, the next thing you're going to do is plot some graphs. So let's have a look at the sort of graph that you're going to be plotting. So let's have a look at graphing. This is taken from the AQA Practical Handbook, and there's very specific rules that you should follow. Obviously, you're going to label your axes, and crucially, you're going to title them as well with a unit. This format is the format that you should always follow, both for graphing and for your tables. So you can see here that I've always got my value, then a solidus, and then my unit. Okay. Now I've put it at the top here because that corresponds to all 3 of these. Here for the extension, I've just done delta L in meters, mass in kilograms, force in newtons. You've got to have clear, sharp data points that definitely indicate a single position. So you can't have sort of circles, for instance. You've got to have your separation such that each of these lines actually represents a value. So if this is 30, then that's 25, that's a definite value. If this was 30, each one of these, this would be 23 and a third. No, it wouldn't be if this was 30. I've got 4, so that would be 2.5, so that would actually be okay. But you need to make sure that you don't end up with these being sort of a non-definite value, like a third or a sixth or something like that. So these are the absolute rules. Your graph has got to cover over half the paper. Your points count as the graph. So effectively, if your data points don't cover half the graph paper, you've done something wrong. So you need to make sure that your scale is such that you're definitely going to cover half the paper. Absolutely fine to have false origins. So this one doesn't have a false origin, but if you need to put false origin in, do it. So obviously you need to have all of the data points on the graph, and it should be clear where your false origin is if you're going to put it in. So you've got normally mark it with a little squiggle or with dotted sort of line. This is perfectly acceptable because it's clear here that you've got false origins and you've actually put them in. So you don't actually have to have that 0 with a squiggle if you want to start it, because of course your axes can start anywhere on the graph you like. See? So convention, they start on 0, 0. So crucially, we want to see that your graph is covering half the graph paper, so your data points cover half the graph paper, that your graph includes all of the data points, that those data points are each marked very, very clearly, that each of the axes are marked well with the values and with a label, that the spacing between each value on an axis, i.e. your scale, is a sensible multiple, so that each line in the graph paper actually corresponds to a definite value. And if we have a quick look at axis graphs, you should be able to see what is done. We're working comp. So here you can see that we've got, okay, it's not enough data points, but everything is nice and cleanly drawn. We'll talk about line of best fit in a moment. Got good labelling, and the data points cover over half the graph paper in both directions. You may want to read the AQA Practical Handbook, but we've given you a little aid memoir of what we're expecting on the lab script. Right, when it comes to plotting a line of best fit, because that's what you're going to do next, you're going to want to follow some of the rules. You want a thin, clean line drawn, and then when you go to calculate a gradient, you want to use as large a triangle as possible. What do we mean by that? So, okay, this is a printed line, but we've got a single line, so you might need to use a longer ruler if you've just got a 15 centimetre ruler. That's often not long enough. And if we look at this, we've got an equal number of points above and below, so our line of best fit is a true graphical average of the data points that are fitted. Here we've got a triangle that is about as large as you can get. Happens to fall on the data point, but that's not required. You want to make it, we could have even made it larger still, could always gone up to here. The reason why you're doing that is because in physics, the bigger the values that you're using, the smaller the percentage uncertainty you have of that value. And that's a key measure of the reliability of what we're actually doing. Now, obviously, this gets a bit trickier if it's a curve, but today everything's straight lines. So let's have a quick look at the sort of results you're likely to be getting. So you'll end up with 3 lots of data, 3 graphs. In Excel, you don't get to draw the triangles, it just puts the trend line in for you. You're obviously going to do this by hand. Each of these graphs will be a full A4 graph paper. I am reasonably sympathetic if you wanted to put the 3 onto one graph. It means that only one will be able to satisfy the rules, so it's cheating, but it does give you a nice comparison of the 3 trend lines. Obviously, you could just have a look at the 3 gradients and go, okay, single was a K of roughly 0.23, the parallel looks like it's roughly double, and the series is roughly half. Well, that's what we're kind of expecting. So each of these would be an A4 sheet. Maybe do one each of those, and then you could always do an extra one to plot it to do a comparison. This is quite nice because you can see that there's the single, there's the parallel, and there's the series. So once you've done the graphs and done the gradient calculations, that is all of the formal analysis that's required for this experiment. But what we've done is we've added in something to try and make you think about it a little bit more. And we've got a series of questions, and for each of the bullet points, you need to make a comment in your lab book. So, do you think which of these elements is part of y corresponds with y equals mx plus c? Well, I've already said, so if you've got the force on the y-axis, the delta on the x-axis, so you've already thought about what the gradient's going to be. And I'm not going to go through all these now, but you're going to read each one of these and just make a comment in your lab book corresponding to each of the bullet points. Sometimes our lab scripts do have this kind of very structured discussion. Sometimes the analysis is so long that we don't really ask you to discuss it in any great detail. My graphs are surprisingly all very, very nice and straight, and I've got my points just slightly above and below, but considering I've slightly cheated in how I've generated this data, it's not surprising that I've got a very, very, very good straight line of best fit. If you've done your experiment well and taken careful measurements, you also should have really good straight lines. The springs we're using are pretty good. Whether you will have exactly double and half will depend on how closely matched your springs are for your spring constants, but they should be pretty good. But you can talk about anomalous points and random errors, and this is basically trying to get you to think about where might error creep into your experiment. And then at the end we've got a nice little conclusion where you're going to copy out and say what the spring constant of a single spring, series springs and parallel springs are. And believe it or not, that's the end of this. Please, when you do this experiment, do everything nice and carefully. You improving your experimental technique will only come about by you carefully applying what you're meant to be doing in each lab.